Good afternoon, fancy meat computers. How's everybody today? I hope you're doing fabulously flabberistic on this flatulous Friday. Good. Concurrent viewers currently 8. Let's see. Let me see if it's just a little. Let me see if it's if that's accurate or not. Suppose I need the link, don't I? Ugh. Oh, I should check for announcements anyways. Password incorrect. Fake news. Okay, so it looks like nothing recently. I did some stuff Wednesday afternoon. So officially moved the due date of Project 1 to October 10th. Reworded a problematic passage in A assignment to question 4B. So get the new version, please. And assignment 3 is now available. Due date is October 3rd. Yeah, so there we go. Quick question about assignment 4B. Are we to make functions that turn whatever expression terms were given into the grammar? No! You are simply to write a term in the grammar and give it the type of the expression. It's more like a constant as expressed in UAE. You're not transforming anything. You're not supposed to take a string and turn it into the grammar, because that's parsing, which you're going to have a whole course on parsing if you take 3TB3. So we're not covering the transformation of strings into abstract syntax, although we are going to understand what each of those things are. Similarly, we're not going to cover the generation of object code from abstract syntax trees, because, again, that's when you take compilers, that's where you're going to get that information. This is just the mathematical foundations of programming languages. So, yeah, that's my answer to that. No, you don't have to write a function that turns one thing into another thing. You just, that's just the easiest way to write an expression and force Haskell's type checker to type check it, because if it doesn't type check, you will know that you haven't done the grammar out correctly. So, yeah. For assignment 3, question 1, I think the table is missing. Oh. Well, I think yeah, I'll take a look. I'll take a look at that. Thank you for that. I removed a question. Hopefully, perhaps I did not remove all of the question that I should have. I'll take a look at that, thanks. I removed the question because A3 would be a long time to do, so I made it shorter. A3 table? Question mark? So basically, it would be write a function that would take successor 0 and return 1. No! That's evaluation. We haven't done evaluation yet. Yeah, you're not... No. You're not, like... You're not supposed to take a string and turn it into terms of the grammar as expressed in the grammar. You're not supposed to take the grammar and evaluate it to, you know, whatever you consider to be the correct evaluation, because I'm going to tell you right now, successor 0 is not 1. That would be mapping successors to natural numbers, and we're going to be doing operational semantics, not denotational semantics. So that, like, mapping successor 0 to 1 would be an example of denotational semantics rather than operational semantics. So we're going to do, like, the values are already in the terms of the language. You don't need to refer to any exterior values, such as the natural numbers. So yeah, no, that's... No. The purpose of question 4 is not any type of transformation. It's simply writing the expression and having that parsed by GHC. I almost said GCC because I'm also teaching C this semester. You don't really know what encoding expression means. It is typing them out and putting them in, like, type it out, give it a name and a type, right? That's what encoding an expression means. Yeah, you also have to make a term that is not 0, because 0 already has meaning in Haskell. So, and it says pretty specifically in the question that if any of your terms have name conflicts with Haskell's own inbuilt things like true and false and 0, you have to come up with your own ones so that there's no namespace conflict. But yeah, okay. So, seems like things have died down on that front somewhat. So, let's continue on with our lecture material, shall we? Because we've got a lot to cover and not a lot of time to cover it in. So, last time we were talking about Boolean evaluation. That is to say, the semantics of Boolean, the semantics of the Booleans. This is the small step semantics of the Booleans under UAE. We went through, so we established this as a series of rewriting rules, or, rule schemas. So now, since we have rules, we can use them in the same way that you would use laws of natural deduction inside of a larger logic. So you can actually perform things like you can find out what something evaluates to by using natural deduction style proofs, which brings this class much closer into the territory of formal logic, as according to the Dr. Farmer definition, rather than this is formal proof rather than traditional proof, because, look at it. See how formal it is? It's amazingly formal. There's so much form going on right now. All the form. You might say it's form all. Bad pun, I apologize. So, the other important point from the previous section that we need to get straight is, notice that we have a rewrite rule that allows us to substitute the conditional of an if statement for whatever that conditional will evaluate to after one step. That is, that's an important one. Otherwise, if you have, if your if conditional is not true or false, then you can't deal with it. So you need that. But conspicuous by its absence is similar rules for T2 or T3. The reason that they're not included is because if we include them, the the operational semantics become non-deterministic. So with the semantics as they're currently instantiated, all the profs are making dad jokes. So as these rules are currently instantiated, no matter what term you're trying to evaluate, there's always only one rule that is applicable to it. And it's like, in this class, when I make a statement like that, you need to say, ho ho ho, you gotta prove that property. So guess what, folks? That's what the whole determinacy section is all about, is proving that property. But first, we need a new form of induction. That's right, folks. More induction for your sweet, sweet brains on this wonderful Friday afternoon of, probably one of the last nice weekends of the year. Because apparently this winter is supposed to be especially long, cold, and snowy. So, oh, full screening. Yeah. Sorry. Should find the shortcut key for it. Full screen mode. Control Shift F. Okay. There we go. Sorry, Joe. So, induction on derivations. So, we have derivations. We have this idea of derivations. We also have this idea that you can have a chain of derivations. So, once we have a series of things which follow on from other things, our natural thought is, how are we going to use induction on this? So, fact. T evaluates to T prime is derivable if and only if there is a derivation proof with T evaluating to T prime as its conclusion. This fact can be used to reason about the properties of evaluation relations, or the evaluation relation. Induction on derivations. If we can show that, A, given that some, that should say some, given that some property holds for all subderivations, if we can take the fact that a property holds for all, if we take an assumption that a property holds for all subderivations, including values, and we can from that conclude that it must hold for the superderivation, that is, the derivation that has the subderivations as its subderivations, then we can conclude that the property holds for all possible derivations. Here, subderivation is a derivation occurring after the derivation at hand. So, in example 1 above, the E if true is the derivation, and E if false is its subderivation. So here, E if true, this is the derivation. E if false, this is the subderivation. You perform the first one, and then you perform the subderivation, or the second derivation. It's called sub because these proofs can branch like it does in this one. This guy is like a subderivation of the, this guy. So if you think about these things in terms of inference rules, you can have multiple subderivations if you have multiple premises on top of the line, right? So that's what subderivation means. So, good. Let's talk determinacy. Determinacy is an extremely important property of programming languages. If it's not determinate, okay, so cast your brains way back to your first lecture of 1MD3. What was in the slide? What makes an algorithm, what makes a computer algorithm and a computer algorithm? It needs two things. It needs to be implementable, and it needs to be unambiguous, right? It needs to be in the terms of the machine language, and you need to be able to follow from one step to the other without any question as to what the next step should be. This is what we call the property of determinacy. So, did I misspell derivation? Derivations? Derivation. That's funny. Yeah. Well, I actually did spell check it, so maybe that is, like, a proper word. Is induction on derivations complete induction? If it is it induction on depth or size? It's not induction on depth or size. It's induction, like, on the derivation relation itself. So we say, we have all these subderivations. We say this property holds for all subderivations. Then we prove it has to hold after the current derivation. And so the current derivation has that property too, so that all derivations have it. But it's not, like, it's interderivable from size or depth induction, but and we're definitely more in the complete induction. Like, in the same way that structural induction is like a form of complete induction, induction on derivations is a form of complete induction. But, it's kind of like, if you're going to have anything as your, like, point of reference for induction on derivation, you should think of it as being a form of induction on structure, where the structure is a tree formed from successive applications of the derivation. That's going to make more sense once we start getting into abstract syntax trees as well, because that is how it works with abstract syntax trees. That's how you evaluate an abstract syntax tree, is you perform these derivation steps on it. Cool. Isn't this anti-symmetry? Let me think here. Oh my god. Yes. I think so. Isn't this anti-symmetry? That's, you know what? Control-Shift. Let me pull up the, oh my god. Now I have to look. Is this anti-symmetry? If it is, then I should have put that in the slides and noticed it. Preliminaries. Oh, that's the text file. There we go. Anti-symmetry. S relation T and T relation S. Aha! Okay, so it's not quite anti-symmetry. So anti-symmetry is SRT and TRS implies S equals T. But notice we've got a T prime and a T double prime here. So no, it's not anti-symmetry. Yeah. So, all right. Again, we have to press on. I have to finish this proof today. So, theorem, determinist. Oh, by the way, if someone in the chat could just let me know when we're 5 minutes out from the end of class, because I can't see my computer's time. Oh, I guess I could just use my phone, eh? Okay. So, determinacy of one-step evaluation. As an exercise in induction on derivations, let us consider the following theorem. Theorem, determinacy of one-step evaluation. T evaluating to T prime and T evaluating to T double prime implies that T prime and T double prime are the same term. That is to say, if a term T evaluates to T prime and the same term evaluates to T double prime, T and T prime and T double prime must be the same term. Another way of saying this is there, basically a corollary of this is that the same rule must be used to get you from T to T prime or T to T double prime. Another way of stating this rule is that for any particular term, only one relation rule will apply to it. That's that's sufficient to prove that the term must become that the terms must be the same as well, right? If there's only one relation you can use, then obviously the term has to be the same at the end. So, proof of determinacy. We will prove the above theorem by induction on a derivation of t to t prime. T evaluates to t prime. We will assume the desired result for all smaller derivations. We will then perform case analysis over the 3 available evaluation rules. I would like everybody to please pay attention to the next 6 slides or so, because there is a question on the assignment that asks you to do this. Like, to produce almost precisely this proof, but with arithmetic stuff thrown in as well. So you get 4 additional terms you have to do the case analysis over. So, note that this is not induction over the length of a derivation sequence. This technique bears more resemblance to structural induction than to complete induction. Although, again, all forms of induction are interderivable. We're going to go through this one in quite a bit of detail, so buckle up. Pacific Cod, you just made me chuckle and, like, snort a drop of tea onto my cardigan. So thank you for that. It's like, hey Siri, set alarm for... Hey Google, hey Siri, set alarm for 1:20. Yeah. My God. And then if we could get Alexa in there, too, that would be... Yeah. So, just a reminder of the thing we're trying to prove. We can make certain determinations about our cases based on the derivation used in t to t prime. That derivation must be one of the following. It has to be either E if true, E if false, or E if. There are no other rules. So let's start our case analysis with E if true. If E if true was the last derivation, we know that t must be of the form if true, then t2, else t3. That must be what t looks like. So this is what we're doing. We're getting, like, so from our case analysis over the different relations that this guy can be, we can make, like, we can use the premise, like, we can use that to determine what t must have been. And that's going to be absolutely critical for these types of derivations. Hey Siri, play Ride of the Valkyries. It doesn't work in reverse. So, anyway. So we know that t, our first t that we're going to analyze, must be of this form, right? So, in order for t1 to not equal t2, we would need to apply a different rule to it, other than E if true. So let's examine the possibilities. Right, so, so t1 and t2, I'm sorry, that should be t prime and t double prime. So, in order for t prime to not equal t double prime, we would need to apply a different rule to it other than E if true. So let's examine the possibilities. When it refers to the last derivation, what does it mean? We're going to get to that. So that inductive step doesn't come into it until we do the case analysis for E if. That's true. Why must the derivation be one of the following? Because those are the only derivations in the system. Right? We only have 3 evaluation rules in our operational semantics. We only have 3 of them. So that's why it has to be one of those 3. So, stop distracting me. So, so here are the other possibilities. So basically what we're saying is, in order for t1 and t2 to be different, this derivation must be something other than e if true. So let's see if e if false works. So e if false. This strategy may only apply if the conditional term inside of the if statement is false. Since we have determined that it is true, this is not possible. So this is not a legal strategy. So we have determined that this arrow cannot be e if false, right? So with e if, this strategy can only be applied if t1 can be evaluated. Since t1 is an element of the set of values, that is to say, it is a member of our set of values, further evaluation is impossible. True doesn't evaluate to anything. There's no legal strategy that turns true into anything because it's a value. Therefore, e if it cannot be used to evaluate t double prime, or t to t double prime. Therefore, the evaluation step, the evaluation relation in t evaluates to t double prime must be e if true. Therefore, t prime is equal to t double prime in this case. And just because this is the way we go, we are going to say, because this is a traditional proof, rather than detailing all of that out with just e if true and e if false reversed, playing the reverse role, we can just say the argument to make the case where we start the case analysis for e if false is symmetrical to this one, so we don't need to do them twice. Because if you understand the one for e if true, you understand the one for e if false. So we are proving determinacy for UAE, and hypothetically, we would have to do the same thing for some other syntax. Yes, hypothetically, as in definitely, and on assignment 3, and other syntax is in this other oh, I just revealed my meme. Aw. This is the other syntax. So, where were we? Yes. There we go. So, now let us consider e if. We know that t must equal if s1 then s2 else s3, and that via e if t prime must equal if s1 prime then s2 else s3. So this is what we can deduce from the form of e if. T must be of this form, t prime must be of this form, and we must have some kind of evaluation from s1 to s1 prime, right? These are the things we know, right? So, good. We can apply the same we can apply the same argument from the e if true case to this case as well. We know that the only valid rule to apply to t becomes t double prime is e if, right? Because it's of this form, we know that s must be capable of evaluation. Therefore, we know it can't be true or false. Therefore, we can say that the only rule which gets us from t to t double prime must be e if, right? We know that t double prime is equal to if s1 double prime, then s2 else s3. So we have access to the following premise, right? S1 becomes S1 prime, right? So we're able to pull S1 becomes S1 double prime. Please ask me to slow down if I'm going too fast. Would you mind reiterating how I picked t and t prime in that last proof? Okay, so t here, if we go back to our semantics, right, it's picked right from here, right? in our semantics, we have a rule that if we have the premise t1 becomes t1 prime, then we have the conclusion if t1 prime, then t2, else t3 becomes, we've got these guys as well. So if we rewrite this, I changed it to s's so that it was less confusing on the new slide. But if you rewrite like the t's here to s's, and then you make if t1, then t2, else t3 into a t, and then the second one into t prime, then that's how I derived these terms, right? I just took this guy and I just said, yep, we've got that, right? Where are we? There we go. So, this is insufficient to prove our final case, right? So, basically, we've got a problem, right? Because we've got, so basically the overall form of t1, t prime and t double prime are the same. However, we have this issue of s1 prime and s1 double prime, right? We've got s1 evaluates to s1 prime, and we've got s1 evaluates to s1 double prime. But if these are different, then that means that t prime and t double prime will also be different, right? Because they contain these terms. So we have s1 becomes s1 prime, and s1 becomes s1 double prime. But in order for t prime to be equal to t double prime, we have to show that s1 prime is equal to s1 double prime, since that is the only point of difference between t1 or t prime and t double prime, right? So we haven't needed the induction hypothesis so far, but here it is. We assume for all subderivations of t, all subderivations of t becomes t prime, that s becoming s prime and s becoming s double prime implies that s prime is equal to s double prime. And there we have it. Since we know that s1 becomes s1 prime and s1 becomes s1 double prime, we may conclude that s1 prime is equal to s1 double prime. That exclamation mark there is just for emphasis. I should remove it, but it's not an operator. That's just like, ha-ha, eureka! That's the eureka exclamation mark. So, s1 prime equals s1 double prime. So, both t prime and t double prime must be the same term. Therefore, the inductive step holds. So, when I say subderivation, this is a subderivation. All right? Good. For completeness, we should also address the base cases briefly. In this case, the base case is the final derivation, which will yield a value rather than another expression. The only derivation rules which can yield a value are E if true and E if false. A very similar argument may be employed to show that t becomes t prime cannot use a different rule than, oh, I'm missing a t. T becomes t double prime because of the guard term of t. Because the guard term of t1 must be a value, which means it must be irreducible, because this is the final evaluation step, and 2 can either be true or false, but not both, because of our language definition. Basically, in order to be able to evaluate a term to two different values, you would need a term to be two different values at once, which of course doesn't exist in our language. We can therefore conclude that both our base case and our inductive step hold, quod erat demonstrandum. So, there you go. And now, I'm going to hold for questions, and next we're going to talk about normal forms. Any questions? It's a subderivation because it was a derivation that equate that t to t prime depended on. Yes. Yep. Again, a subderivation is like the next derivation that you would need to do if you were doing a natural deduction proof, right? So think about if you were evaluating that according to natural deduction, right? The next thing you would have to do would be to derive S to S prime, S1 to S1 prime, right? So that makes it's a subproof. Or that's a subproof, and the whole thing is a subderivation. So, yeah. Okay, we're gonna move on. Normal forms. You fools! This isn't even my normal form. Because that's how they talk in Dragon Ball Z, right? So, as programmers, we know how an expression is evaluated is much less interesting than what it evaluates to. A term t is in its normal form if no evaluation rule applies to it. That is, there is no t prime such that t evaluates to t prime. For the present system of untyped booleans, we know intuitively that the normal form of all terms is t or f, true or false. So this is an important piece of nomenclature. This is an important term that you need to remember because we're going to be using it a lot in this course for the remainder of this course. Normal form, a term which cannot be further evaluated. So, theorem! Every value is in normal form. Let's do a proof. This slide deck is not 3IO3 approved. Yeah, it's been a while since I did 3IO3. I don't care. Is it because of the memes? What makes it not, like, legal tender? That's interesting. But, yeah. So, theorem. Every value is in normal form. Our set of values is, in this case, just true and false. Given that a term is in normal form if no evaluation rule applies to it, and given that we have no rules for evaluating true and false, we can conclude that they are in normal form. Shortest proof in the world. This is somewhat trivial to demonstrate, but we need to be careful as we add terms to UAE not to disrupt it. So, basically, the way that you maintain this property is by not adding evaluation rules which evaluate values. To meme maximum. Ha! Use of unapproved comics? Use... Approved comics? That's like approved pranks. Like Kipling having approved pranks. Man, like, y'all need some chaos in your lives. Okay. So, also in Project 1, we have a numeric value, which has a successor of normal numeric value as one of the types. No, because in that case, we're defining successor as if you have a chain of successors applied to 0, then that's considered a value. That's something that we're going to get into when we get into arithmetic. Only XKCD and Dilbert are approved. Y'all need to have more fun in your lives. If Dr. Machio wants to come after me, he's welcome to try. So, normal form. If it's in normal form, it's a value. Also, what's wrong with what's wrong with that? That's funny. Man, it's a rough time to be alive if you're a person with a sense of humor. So, if t is in normal form, then t is a value. So this is kind of the inverse. Every value is in normal form, so now we want to conclude, if it's a normal form, is it a value? Can we conclude it must be a value if we've reached normalcy, right? Yeah, so successor... Okay, I'll talk about the arithmetic when we get to the arithmetic, okay? Oh my goodness. So, proof. Let's say that t is not a value. We seek to show that t can't be in a state where an evaluation rule does not apply to it. Let's also introduce an induction hypothesis and assume that all subterms of t are either in normal form or can be evaluated. If t is not a value, for the present subset of UAE, there is only one term that is not a value. Therefore, it must have the form if t1, then t2, else t3. Whether or not any evaluation rule applies to it depends on what t1 is, right? So, for t1, the possibilities are it's either true or false, in which case E if true and E if false apply, respectively. Or, if neither of those two cases apply, since the two cases above take care of the cases where the subterm t is a value, via the induction hypothesis, t1 must be able to be evaluated. This means that E if applies to t. Therefore, if t is not a value, it can be evaluated, meaning it is not in normal form. Therefore, values are the only thing in normal form. Therefore, if it's in normal form, it's a value. Ta-da! We will see later that this is not necessarily the case for all languages. Successor 0 cannot be evaluated, but it is also not a value. So, except if you redefine values, we're gonna, it's the trick that they pull to, the trick they pull with the arithmetic semantics is to redefine, to define a new set of values called numeric values, which includes successor. But yeah. Thank you. I thought it was funny. Thank you, Joe. So. Therefore. Alright, termination. A property of extreme importance when it comes to programs in various programming languages is the property of termination. How much time do we have? 10 minutes? Given... I'm going to skip ahead and do the arithmetic section. I'm going to introduce arithmetic operational semantics, and then we'll come back and do termination. Because if you want to get started on assignment 3 before Monday, then or before Tuesday, then you're going to have to have this information. So, reading, writing, and arithmetic. How many layers of irony are you on? Like maybe 5 or 6 right now, my dude. You are like a little baby. Watch this. Suck. There you go. Another unimproved piece of humor. So far, we have only been concerned with the Boolean terms of UAE. Time to make things more complicated. As we construct our semantics for arithmetic operations, we are also interested in the problem of nonsense programs. So with just Boolean terms, it was actually impossible to create nonsense. That's interesting, right? Like, if you take the Booleans alone, it's actually impossible to create a program that, it's impossible to create an expression using only those terms that would not correctly evaluate, or it doesn't have an evaluation, or is nonsense in some other way. There's no such thing as a type error if there's only one type. That's what I'm trying to say. Surreal memes transcend approval. Agreed. So, although this is still an untyped expression language, terms have limited applicability. Applying a term to an incompatible term will create nonsense. When a term is in normal form but is not a value, we say that the term is stuck. So, basically, imagine this scenario. If 0, true, then true, else false. Right? That can't be evaluated because 0 cannot be evaluated to anything else. Right? There's no rule which gets you to anywhere else from 0. So if 0, then true, else false is in normal form, despite the fact that it's not a value. So, yep. So, here are our semantics for arithmetic. First of all, we have a new set of we have a set of numeric values. So values are a subset of numeric values are a subset of values. We have 0, that's a numeric value, and the successor of a numeric value is a numeric value. That's how they get around the problem of only 0 being a value and successor being a function and not a value. It's like, that's how they do it. They just throw it in there. So, here are your evaluation rules. Number 1. Successor of t1 can be evaluated to the successor of t1 prime if you have t1 to t1 prime. The predecessor of 0 is 0. That's an interesting one, because that is the difference right there between operating over the natural numbers and operating over the integers. That rule right there. So, yeah, as I said on Piazza, the 0 in this semantic has this property where if there's ever any predecessor applied to it, it kind of just schwarps it up. So, that should be fun for headphone users. So, if you apply predecessor to the successor of a numeric value, notice not just general successor, but numeric value specifically, you can get the numeric value out of that. It evaluates to the numeric value. So the only purpose of predecessor is to delete a successor. And you can perform substitution. If t1 is not in normal form, then you can substitute it for one step of evaluation. Is 0 successor of a numeric value evaluates to false? Oh, I skipped one. Is 0 of 0 evaluates to true? Successor, yeah. And if it's not 0, it's false. And of course, it has to be a numeric value. And we can perform the same substitution that we do with epred and esuc. Why? Why did I do this to us? I didn't do it. The textbook did it to you. Ha. So, in order to properly define our semantics, we need to be able to distinguish between Boolean and numeric values. To this end, we create two syntactic categories. Well, we reuse an old one and we create a new one. V and NV. For Boolean and numeric value. Oh, envy, like envious. Right, got it. Items of both categories have all the properties of values, such as correspondence to normal forms and uniqueness. Note the inclusion of the successor of NV in NV. This means that if we have an unbroken chain of successor terms terminating in 0, that constitutes a value. I see the spelling mistake. This asserts the natural numbers as being values. So successor is defined in both T and numeric values. Isn't this ambiguous and non-deterministic? Well, no, actually it isn't. Because well, that would actually kind of be giving away the solutions to the homework. Part of the homework is to extend the proof of determinacy to this new set, right? So you'll find out for yourself when you do the proof that actually, like these are just subcategories of terms, right? Like numeric values and values, they're not like, we distinguish them from like the terms, but they're still like they're subsets of the terms. So it's not like we've introduced two successors, right? It's just, we recognize a difference when the term that you're successoring can be evaluated and when it can't. And when it's a natural value. Like, successor of false is still nonsense. Yes. So, how much time do we have? Okay, we have enough time for this. Consider the following expression in UAE. Is 0 successor, predecessor, successor 0? Which rule applies? E is 0's successor, E is 0, both or neither. It would take too long to give away the solution in this lecture. Besides, I basically gave away the hint. Like, all you have to do for this is, like, take the case analysis and expand it by the new rules and terms, and then there you go. Time, 2 minutes. So, what do you think? What do you guys think? Which, is it one? Both? Is it this one, both, or neither? Come on. Chop, chop. I will tell you. It's this one. E is 0. Because this guy can be evaluated. You can't apply E is 0 successor because this guy in here is not a numeric value. You can know it's not a numeric value automatically by seeing that there's a predecessor already in there. So this guy can be evaluated, which means that this is the one you're using. There you go. So the answer is E0. We can't use E0. We can't use E is 0 successor because successor predicate successor is not a value. It can be evaluated. If this rule did not require a numeric value, the rule would also apply to evaluate successor terms. This would be a rather nasty case of ambiguity, destroying our language's determinacy. Destruction of determinacy is something to avoid at all costs, even if we could show that it doesn't break the determinacy of multi-step semantics. So the thing we jumped over was multi-step semantics. The Coles Notes version is, now that we have an evaluation, like a single-step evaluation relation, we can also define a multi-step evaluation relation, which is like, where is it? Yeah, here it is. It's just, we write it arrow star, so it's like, you know, if you take the transitive closure of the evaluation relation, you end up with a multi-step evaluation relation. So, yes. So yeah, good. That's time. I will take any questions. Right, it's cool, right? That's a successor chain is a numeric value, but it can't have any values in it. Yeah. Yeah, exactly. It has to be composed entirely of numeric values, otherwise it's not a numeric value. Because the definition of a numeric value is recursive, right? You're either a 0 or you're the successor of a numeric value, which, you know, the only one that's not a successor is 0, so you have to be, you know. Yep. Yeah. So that's what provides this, that's one of the things that means this language is still determinate. We haven't broken determinacy. However, if you didn't understand the rules, if you weren't looking at the rules carefully enough, you might look at this and say, oh, you know, successor of some term. Well, the successor of some term, that might be something we could evaluate, you know. So maybe we could have two rules apply at once, but no. Since we are constraining this to only operate over numeric values, and the same with predecessor, we're also constraining predecessor to only occur on numeric values, we retain determinacy. So you have to convert the value to the numeric value by removing the predecessor to allow us to use is, yeah. So, with one exception, successor, predecessor, successor is not a value, it's a term. So it's not NV, and it's not in NV, and it's not in V either. The only things in V, well, technically speaking, the way it's defined, NV is a subset of V, so anything that's in NV is also in V. But the only things that are in V that aren't in NV are true and false, and this is clearly neither true nor false. So this is just a general term. Right? Da. there any other questions? So, in your Haskell project, V is TF0 and successor. So, the way that I did it when I so the problem with data is that it requires exclusivity. So, like, you're not allowed to define the same. You're not allowed to give more than one data type the same label, the same type. So what I did when I did my implementation was I took all of the values and I separated them out into their own data types, their own, dedicated data types. So I ended up with like one type for terms, one type for values, and one type for numeric values. Now, that being said, Haskell is capable of things well beyond my understanding, and possibly someone in the class comes up with, interesting solutions to the problems that are, outside of, like, I want the project to, like, have embedded within it the possibility of using high-level Haskell skills that even I don't know about, So if you can find a very, very advanced way of doing it that's, not the basic stupid way that I did my thesis in, then by all means. Wrapping your brain around things hurts your brain. Well, then, like, it is the recommendation of your prof that your brain remains inside of your skull at all times. You shouldn't be wrapping it around things. That's just probably a good way to, get yourself permanent brain damage. The only thing your brain should be wrapped around is your brainstem. Yeah. Eval show A at EQA. That okay, but I don't think that would that work? Could you have the A2 solutions right after the due date to help with the project? Yeah, I think that's reasonable. We won't wait until it's marked to give it back to you. Yeah, I think that's reasonable. Like, I don't like the idea of assignments having dependencies in other assignments, Like, it's tricky because, like, I thought it was a really valuable exercise to be able to do the grammar out, like, regardless of the semantics, like, when we were learning the syntax. But now that we're introducing semantics and you're doing the semantics, you do need that previous instantiation. So yeah, I think it's reasonable, but not until A2's due date has come and gone, and probably a few, like, the 3-day waiting period afterwards as well for any MSAF people who file an MSAF. And I cannot determine on Monday that there are no MSAFs because people are allowed to submit the MSAFs up to 3 days afterwards. So unfortunately, the absolute latest that I could release that type of information would be Thursday of next week. But yeah. Yeah, the whole idea of the evaluation function in Python in Haskell is that you're making use of pattern matching over your data type that you've created. That's like the whole thing, man. Could we have the solutions to A successor 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 0? Not yet. Not yet. Write it, and we might talk. But no. Wouldn't it be fun if you could just, like, take your solutions to A2, call successor on it, and get the solutions to A3? Wouldn't it be cool if the universe worked like that? Yeah. Yeah, on the subject of the whole Haskell thing, like, how is the Haskell training going? Are you guys getting up to speed with it? Like, have you been looking at stuff? Yeah. Hopefully the resources that I posted aren't completely useless. Oh, that's a... Okay. It's a reflection on my... I thought it was a color distortion, but it's just like some light from somewhere shining on my monitor. Yeah, I hope you kept your work from 1JC3, eh? No. It is on there, because there it is too. It's in the same spot. That is a... Yeah. I wonder what that is. Move my book here, it comes back. Move my book here, it fades out. Weird. Yep. Yeah. So, Jay, like, I sympathize with you. The statement is, for me it was my first time with Haskell, and I don't know if it was the problem, but I just had trouble understanding what the question it was really asking. So, the question is really easy if you can figure it out. Like, the problem, like, it's the conceptual barrier to entry that's the difficult part about question 4 on A2. Once you understand what it is that you can do, what you are doing, you're probably, like, you can probably finish all 3 parts of that question in 5 minutes. Probably less than 5 minutes, but you have to understand what you're doing. Yeah. Yeah, that's, yeah. Like, the actual code is like less than 15 lines of code, for sure. Less than 15 lines of code. Oh, of course, in Haskell, line count doesn't really mean anything. So, you know, you can have extremely complicated things going on that require a lot of brain power, and it's not much text on the screen, you know. But yeah, it's not hard if you know what you're doing. Yeah. Yeah, good. Good. Well, Anyway, so that's me for today. Thank you very much for hanging out, and we'll see you in the next one. Tuesday. Be there or be square.